Hello everyone and welcome on our last day of our digital V-Days. So I'm very happy to welcome all of you to our topic today, calculation, design and LT-SPICE simulation of AC line filters. And I'm also very happy to welcome you, Andreas.
Thank you.
Thank you very much for being here.
Of course. I'm looking forward to it.
Yeah. Andreas will hold the presentation today and also answer your questions. Those will be at the end of the session. You can ask us all your questions in the chat and then later on we will go through them. And if we don't have the time to answer all your questions, then we will send you an email with the answers. And if you have any other question, then just email us. We are there for you. Then also we will share the handout with you, so you will also get the presentation you will see. And I think with that's everything from my side. Andreas, have fun.
Thank you.
And enjoy it.
All right. A very warm welcome from my side as well. My name is Andreas Nadler. I'm Field Application Engineer in Bavaria, Germany. And I'm happy to present you this topic today. So all the calculation, all the math, all the simulation I will show you today is not only valid for AC line filters, but also for DC-DC line filters. So that means unimportant if you calculate a filter for a DC-DC converter or for an AC-DC converter, you can use these calculations and these simulations as well. All the relevant information I also, compromise in a EndNote, a new one, ANP 015. You can download this on our webpage in German and in English, and you will find also the detailed information which we also share now in this seminar. Well, our agenda for today, we will look short at the source of interference for AC-DC and DC-DC, converters or sources, as well as for the required components for filtering. I will show you the difference between a one-stage and a two-stage filter, and maybe where is the benefit of the two-stage filter compared to the one-stage filter. I will show you how to calculate this, how to simulate this with LT-SPICE, because it's a free simulation tool and it's powerful enough for to get a good estimation in the pre-development. And I will show you, of course, then at last the measurements from the lab in conducted emissions and radiated emissions, and of course some hints to how to make a good layout for AC-DC filterings. Of course, just for completeness, I will show you a brief overview of our portfolio here. We offer you, of course, complete line filters like the CFLS. But if you want to save some money and would like to include this all on your own PCB, of course, we offer you the completeness for one-phase up to three-phase filtering from capacitors, from single-line chokes, three-line chokes, and so on. Just contact us or ask us if you need any support here. We are very happy to help you in this topic. Of course, now, what's the source of interference for our demonstration here? I choose a DC to DC flyback converter. Just for safety reason, I do not choose AC-DC, so I can touch here anything, anywhere, so no problem at all. And there's no difference if it's an AC-DC or a DC-DC, because it's in both cases we have just a higher or lower input voltage, but the principles in common mode and differential mode and all the filter principles are the same. We have a switching frequency of 300 kilohertz and an input voltage from 24 and the output voltage of 5 volt at 25 watts. So nothing special, just a standard isolated flyback converter. Just for completeness also, a few words about differential mode, common mode. Differential mode, the earth is not included in your system or in the current path of the interference. And common mode is the more critical and more difficult to filter and to figure out because there always the earth path is included in the return current in your system, and this is most for the most engineers the more difficult interference current to comply with. So important for differential mode, the current paths are like in your schematic. That means it's pretty easy to follow. We can filter this with LC, pi, T topologies, capacitors between the line and the neutral, or capacitor between plus and minus. And usually the di to the t is the dominant root cause of the interference current in differential mode. So that's pretty easy to filter and to calculate for the most engineers. Common mode is usually a little bit more tricky because the current paths are not like in your schematic. They're always traveling around, let's say, parasitic paths, and these paths are usually capacitive paths. So therefore, we're only talking about usually a few microamps, not milliamps or amps. It's pretty small currents. The return paths are pretty large. And you can filter this only with common mode chokes, Y capacitors, shielding, increasing distance, and so on. But that's then the only way you can do it. Or you decrease your dV to dt. That means you have to switch slower the voltage. That also means then you lose efficiency in your system. And mainly in most cases, it's a radiated issue for many customers. But as we have now for today an isolated topology, the common mode is also a problem at the switching frequency, as we can see on the next slides. So why do we have common mode issues here with an isolated topology? Because of mainly of the coupling capacity or capacitance of the transformer. So during the switch on and switch off transitions of the low side MOSFET, the high frequency currents are traveling over this coupling capacity to the secondary side, and from there, due to the switch node, due to the connected cables, we are forming a capacitor from a few picofarads to earth, and then the currents traveling back to the line impedance stabilization network, and there you get your emission problem or your conductive problem, because there it's measured and coupled out to the EMI receiver. As well, you can have issues with connected heat sinks. There's also a parasitic capacitance, which then acts as an antenna to ground or connection to ground. So with a non-isolated topology, like a standard buck converter, usually, let's say up to 10 megahertz, you do not have a common mode issue. Just in the higher frequencies, then the common mode is getting dominant. But with an isolated topology like here, you will have common mode issues at the switching frequency and above. If you look at differential mode is, as I said, an issue mostly of the high di to dt in combination with parasitic inductance. That means if you have an input capacitor with a high ESL, like an electrolyte, in combination with a high di to dt and a high ESR, you will, let's say, reflect a lot of ripple and noise to the listen, and therefore the listen is then also measured, in the listen is measured as your EMC problem then. Inside the listen, we have two 50 ohm resistors. And if we now, for our experiment, would like to know how big is our common mode and how big is our differential mode, we need a two-line listener. That means we need a listen with two parallel usable outputs, because in most cases the listen has only one output at the same time, and this means you can only measure differential mode and common mode together. You cannot separate them. But if you would really like to size your AC filter in a correct way, you need to know the amplitude of the common mode interference and of the differential mode interference at a certain frequency, because then you can really size the Y capacitors, the X capacitors, the common mode choke, and the, let's say, leakage inductance in a proper way. Because what you do not want is to size your filter too big, because then you lose money and you lose space on the PCB. If you do it too small at the beginning, you have to invest again time during the EMC or after the first EMC test, and this is also not really convenient for you and your company. So if you look at the differential current path, we see the current path in the differential mode, the red one, is traveling from the source of interference to the listen, and it travels with the two resistors in a row. So that means we have two resistors, 250 ohm resistors in series. So for differential mode, the listen impedance is 100 ohm. This is important then for the simulation and for the measurements. For common mode, where the traveling path is through the parasitic capacitance, we see the common mode is traveling on both lines at the same time in the same direction. There is no phase shift between, like in differential mode. And in this case, the blue, let's say, currents traveling in the 250 ohm resistors in parallel in respect to PE. That means for the common mode, we have 25 ohm listen impedance, which is important for the simulation, for example. So that means if you would like to measure this with a scope or let's say with a hardware combiner, if you like to measure the common mode, we have to add the two current the two voltages from both terminals. If we would like to have the differential mode, we have to subtract one from each other. And as we have the listen voltage divider, we need to divide this by 2 in the end to get the correct result. So if you have a oscilloscope like the Rohde & Schwarz, MXO or RTA, whatever, you can do this with the math channels. So you can use channel 1, channel 2 to connect them to the RF output of the listens, and then make a division by 2 or use the attenuation of each channel to attenuate this by 2. Okay, now for a filter perspective, it's important from a, let's say, simulation point of view. If you have the common mode, we have a noise source impedance, which is often not really known. We have the two Y capacitors at first. This is important from the simulation and also from the layout and from the, let's say, placement point of view. We have to place the Y capacitors always at first to shunt most of the common mode currents back. And then we have the common mode impedance, the main common mode impedance of the common mode choke. And this is with respect to a 25 ohm impedance inside the listen, respected to earth. If we have the differential mode noise source, it's usually the input capacitor of your system. So it's usually pretty low noise source, around 0.1 ohm. You can, if the capacitor is really at this place, then you can really take under 1 ohm. Then we have our leakage inductance or our, let's say, differential mode choke. And then we have the X capacitor. And then we form the LC filter from another, let's say, vice versa, like in a common mode. And the listen impedance is 100 ohm in this situation. Important to know is we have different common mode choke cores. Usually you need manganese zinc or nanocrystalline for the lower frequency ranges. For the higher frequency ranges, you use nickel zinc cores. In our example here, we took manganese zinc cores. You see the difference here. Manganese zinc is better in the lower frequency range where we have the highest amplitudes due to switching frequency and to the harmonics. And in the higher frequency range, nickel zinc and nanocrystalline is a good choice. And also nanocrystalline in the lower frequency range is better than the nickel zinc. So it depends on your noise spectrum, how to use or which core material you would like to use. Also, leakage inductance is different. The leakage inductance we use in combination with the X capacitor to filter the differential mode noise. So if you have a core with a bigger distance from each winding to each other, we have a higher leakage inductance compared to ring cores, just for information. Also, for higher frequency, you can use a gapped common mode choke with an air gap. That's air gap is inside here. So we lose attenuation from the amplitude point of view, but we gain a lot of bandwidth for the required damping in common mode as in differential mode. Important from a layout point of view, it's always good to separate the input filter and the output of a power stage. Otherwise, you can have maybe some coupling from the input to the output, and then your filter is compromised. So always try to be as far away as possible, or maybe make some partial shielding in this area if possible. Okay, let's start with the math. It's not that complicated, I promise. So this is my setup for my pre-compliance measurement. You see the Rohde & Schwarz oscilloscope here. We have a DC supply, an isolation transformer for the scope to block all common modes from the grid. I have a 50 ohm self-made listen, a 50 microhenry self-made listen, the filter PCB with the single stage and the two-stage filter, our flyback as a noise source, and electronic load. Everything is on the coupling plane to get the perfect results in terms of common mode comparison to the lab. Important, if you use Y capacitors in your system, you need to connect them with a low impedance connection as possible. That means the best thing is to use, if possible, ceramic Y capacitors. and connect them with a very low distance with polygons as short as possible to the protective earth or to your system coupling plane or virtual P, what you have in the system, depending on what your application is like. Not every application has a protective earth, but then maybe you can do a virtual coupling plane under your PCB where you can shunt back the common mode currents locally. So this is then measured with my test setup in my, let's say, home lab. You see the switching frequency at 300 kilohertz and of course all the harmonics up to 30 megahertz. And I measure differential modes, so one channel minus the other channel divided by 2. I measure 77 dB microvolts, and the limit is of course, or should be class B. So I need a lot of damping, at least 30-40 dB here for differential mode. The common mode, I add one channel to the other channel, so channel 1 plus channel 2. I see the common mode is much more dominant here due to the coupling capacity of the transformer. We see 84 dB microvolts. So we need, for sure, over 40 dB damping here. And if you measure both together, so now I just measure at one channel of the listen and make a 50 ohm resistor at the other channel. And we can see we are getting a little bit higher. The combined one, common mode plus differential mode, we are around 86. And this is what you measure usually in the lab. So in the lab, you cannot see really the difference between common mode and differential mode. But in this case, you see the common mode is dominating the system. So at least 40 dB of damping to get under the limits of a little bit of headroom. This is our goal in this filter. If you use a one-stage filter, you can achieve with an LC part at least 40 dB per decade. So a good way is either to calculate the required damping at switching frequency. And if you now need the required filter corner frequency, you can rearrange the formula, the required corner frequency of the LC filter, where you get at 40 dB damping per decade, because only at FCO this is starting 40 dB per decade damping. You can type in here now your switching frequency and the required damping. So that's in our example for 300 kilohertz and 40 dB required damping. For a two-stage filter, we get 80 dB per decade at the corner frequency. So we rearrange this formula a little bit. We change the 40 to 80, and then we can calculate the required corner frequency of the two-stage filter, which will be, of course, higher. That means the filter components for each stage will be smaller. And this is only valid for a two-stage filter with the same components at the two-stage. Okay, let's do the calculation. We know we need 40 dB. That means with a one-stage filter, we had 40 dB at 30 kilohertz, because 30 kilohertz is one decade below 300 kilohertz, our switching frequency. This our FCO is 30 kilohertz. So that means we can achieve 40 dB if we go one decade below. We have to start with something. And start with something means you have to define at least one component, let's say 3 in the air. But as we all know, the Y capacitors are limited, or limiting our current through protective earth a little bit. So because of touching safety, we are limited in most applications to 3 milliamps, 3.5 milliamps leakage current in our system. So I starting usually always with the Y capacitors to size them not too big. So 4.7 nanofarad is a good choice for starting with the Y capacitors, because then usually you stay below 2 milliamps or in 60 and 50 hertz grids with the leakage current. So we have, as they are in parallel, when they are connected to Earth, we have 4.7 by 2. We have 9.4 nanofarad total Y capacitance. So now we can, as we know, the corner frequency which is needed for this filter, we have to rearrange the formula from the Thomson equation. Therefore we can calculate now the required common mode inductance with this formula, with the 30 kilohertz and the Y capacitors. We get 3 millihenry math. This is not a value which is common, so we choose a 3.3 millihenry. And as all common mode chokes has a wide variety of tolerance, I always recommend you to stay with a good headroom above this calculated factor, because plus minus 20, plus minus 40 can always happen with a common mode choke, depending on the core permeability. So in the next step, we can calculate the actual, let's say, expecting damping, because we have a little bit higher common mode inductance, if you really choose an inductor with this value, we will get around 41 dB with this inductor, with this capacitors. Next step, we calculate the leakage inductance of this common mode choke. This can be done with the differential mode impedance curve. You can use RedXpert for this, and just divide the impedance by the frequency you read it, and it's around 15 microhenry. Then at next, we can, because this is then valid, this is a value we need for the differential mode filtering. This is the line filter for the differential mode. And now we need a capacitor for the differential mode. It's the Y capacitor. And we also rearrange this with this formula, and we get around 1.9 microfarad. In the end, we have 2.2. This is a standard value, and we chose this. And then we can achieve around, in reality, with the components tolerances, when we are close to the calculated one, around 41 dB. The two-stage is pretty similar. We just have a higher FCO. This gives us overall smaller, let's say, components. We have 80 dB per decade. So that means I'm starting with smaller Y capacitors, so I get smaller leakage current and smaller and cheaper components. So only 2.2 nanofarad compared to 4.4 nanofarad. Then our required common mode choke will not be 3 millihenry, it will be only 1 millihenry, which result in a smaller common mode choke. Then our damping is here around, and in the reality 48 dBs, because we calculate 0.6 and we get 1 millihenry. We choose millihenry in reality, so it's bigger than calculated. Therefore, we get not 40 dB, but 48. Next step is the leakage inductance. It's around 6.5 microhenry. Therefore, we can now calculate the X capacitor, which is around then 0.4 microfarad. We choose then a 0.56 or 560 nanofarad type, which is a common value here. Better to stay a little bit above the calculated than below. And this gives us 45 dB for the differential mode in theory. And of course, if we would like to add, you can add also the differential mode, the varistor, which is usually used here with a few picofarads, and the two Y capacitors. But this has no big influence in this calculation. But you can add it in the simulation, because then the simulated insertion loss has an influence in the higher frequency range. If you have a two-stage with not the same component, you have two poles where you have to calculate. So that's also not a big issue. That means you have, for example, a stage with a lower capacitance and a lower inductance for a higher frequency. And for lower frequency damping, you have a higher inductance and a higher capacitance. And therefore, you need to calculate this a little bit separately with these formulas here. We do not go into detail now. You can read this by your own. It's not a high sophisticated math. In the end, you can also simulate this with LT-SPICE to see the two stages. So that means we have at the stage with the bigger components, we have a lower FC corner frequency. Then you get from this corner frequency 40 dB. And with the second corner frequency, with the smaller components, we get the 80 dB per decade, as this is then valid for a filter with two different stages, let's say. That's not a big issue to simulate or calculate. Okay, let's go to the filter schematic. With Altium, developed the two filter stages. The upper one is the one-stage filter with the calculated values. Also, we see here the varistor included here, the Y capacitors, the common mode choke, the X capacitor, and the bleeding resistor. And for the two-stage filter, we have the same. We have a fuse holder, a varistor, and the two stages with the same components. And the PCB looks like this for it. We see here the common mode choke and the Y capacitors, which has the Y capacitors a very low ESL connection to protective earth. The X capacitor, the varistor, fuse holder, and the same at this two-stage filter below. We can see the components are much smaller. Of course, maybe a little bit more space after all, but you will see in terms of EMC, the performance of the two-stage filter is much better. Simulations. We'll see here, I can use LT-SPICE for it. Important, the first one here is the differential mode simulation. So that means I use 100 ohm listen impedance for both stage, for the one stage and the two stage. And I use a voltage source. You can also add in series a resistor if you know your actual noise source impedance. Otherwise, we have an ideal voltage source. And then we have the common mode, the leakage inductance, which is really effective here with the X capacitor. The same with the second stage here. And what we can see, this is important, we have here our calculated damping from the math. It's around 40 to 42. And we can see the one-stage filter starts to decay earlier than the two-stage filter. So in the conducted as in the radiated spectrum, we can expect a better performance of the two-stage filter in differential mode. The common mode, in common mode, I choose a current source, a high impedance, a low impedance current source here, where you can also add in series a resistor if you really know your actual impedance of the system. This is usually depending on the capacitor, the parasitic capacitor here, to the coupling plate of the EMC lab. And we have the Y capacitors at first stage, and then the common mode, and the second stage, the common mode inductance. And this is then referred to the 25 ohm listen impedance. The same for the two-stage filter components. And if you look at the common mode simulation here, we also see the calculated values are fitting good to the simulated values. And we also see here the one-stage filter is decaying faster and gives you a lower overall attenuation than the two-stage filter from the radiated and the conducted spectrum. Of course, I can tell you everything, but I have to prove. This is the reason why we measure this here in Munich in our EMC lab, where you can also, if you are here around this area, you can book hours here with the support of our engineers to make pre-compliance measurements. And we can see here the conducted emission measurement setup with the coupling plate I used. And this is what we measured here. This is the same like I measured with my test setup in my home lab. So I also got there, if I make the combined measurement common mode plus differential mode, 84 dBs. And also the whole spectrum looks good, like compares to my pre-compliance setup. And if I now add the one-stage filter, I get exactly what I calculated and what I simulated, around 41 dB of damping. So I'm pretty good up to this frequency range, but here we see we are pretty close to the average limit. So that means in reality, I would not do this with the one-stage filter, or would at least modify this one-stage filter to get this frequency area around 23 megahertz with a higher, let's say, distance to the limits, to the class B limits here. But therefore, I choose the two-stage filter. The two-stage filter gives you what we calculated, a little bit more in the lower frequency range, because the components were a little bit bigger than the calculated one, but it's fitting well to the simulation and to the math. And we see the big difference here in the higher frequency range. We are around 30 dB better than the one-stage filter. This is because the smaller components have the better parasitic properties in the higher frequency range. And the next setup, or the next measurement, was the radiated setup. We also made in our EMC chamber here in Munich. So you can see the antenna here and the absorber, and here the test setup of really long cables, so over 1 to 2 meter cables, so not shielded, nothing, really open. And this is when we have no filter at all. So the flyback with no filtering. We see a broadband interference, which is typical for switch mode power supplies. We do not see single spikes. We see a broadband, let's say, interference. This is valid for many switch mode power supplies, as they look pretty much the same depending on their cable length and so on. It's a little bit different amplitude and frequency, but it's all broadband. So if it add the one-stage filter, we are under the lines, vertical, horizontal, and quasi-peak, so everything is fine. With a little bit less headroom in this area maybe. If we took the two-stage filter here, we get the required headroom around 8 to 10 dB over the whole frequency range. And this is also a good idea, or this also shows you why it's a good idea maybe to take sometimes a two-stage filter compared to a one-stage filter. So where can be possible deviations between your measurement, your math, and your simulation? Of course, one big topic is the tolerance of the component, especially combo chokes, but also X capacitors, older ones maybe have a bigger tolerance. The PCB layout has a big influence, so the near field coupling, if the components are too close to each other or too close to the power stage. The grounding of the Y caps is not good enough in terms of ESL. So a lot of possible variations why your math and your simulating is not fitting to the reality. And last but not least, you can have from us some filter components. So already we could offer you a filter set with bare PCBs where you can assemble by yourself for AC/DC as well for DC/DC. And this is available with this order code. Just go to your local Würth Elektronik partner and say you need some of these design kits. And that's all from my side. I hope you enjoyed the session and you learned something you can use for the practice. And I'm open and happy for your questions.
Yeah, then, Andreas, thank you very much for the presentation. A lot of information, but very cool. And we also got some questions, I see. First of all, I now want to share the handout with you. So you are now able to download the slides. And yeah, then enough for me for that. So then let's just start into your questions. And here we see the first one. Andreas, how do you handle cooling? Is a two-stage filter easier to cool since the components are smaller or more distributed?
Cooling is first to say you should size your filter that is not required to cool, of course, because mainly it's an RDC topic here. So the AC losses in the filter are usually not the big issue compared to power stage itself. So, but yeah, if you want to cool this, I think it makes no real difference if a two-stage or one-stage filter. A good way to cool a filter is to use potting, some potting materials, because it's a better thermal resistance than normal still air, let's say. So, but yeah, from a pure cooling point of view, maybe it makes not a big difference. Then maybe it's better to choose components from a capacitor point of view and combo choke point of view, which are in the equal size. Then it's easier to pot them or cool them with a fan, for example. But yeah, I would from the beginning I would size them from an RTC point of view that is not required to cool them.
Okay, thank you very much. Then the next question is regarding the slide 18. Is isolation transformer effective enough for rejection of higher frequency common mode noise from mains due to capacitance?
So always my colleague helped a little bit with the slides here.
Perfect.
Okay, the coupling capacitance is a issue during the design process of the transformer. We also, with our daughter company Midcom, designed these transformers. And there are two aspects designing a transformer from the EMC point of view is the leakage inductance and the parasitic coupling capacitance, primary to secondary. And both influence each other. So that means if you would to achieve a lower leakage inductance, then you will achieve mostly a higher coupling capacity, because then you have to intertwine primary and secondary in a very close manner, bifilar manner, let's say. So if you have done a transformer with a low coupling capacity, primary to secondary, most of the time your leakage inductance is higher, because then you separately more primary to secondary winding. So it's always a little bit kind of trade-off. A good idea is then to use the LLC topology, because with the LLC transformer, you use the leakage inductance as a part of the power stage, and you can design then a transformer with the lowest possible parasitic capacitance from primary to secondary. So, but on the most sides, they say higher leakage inductance will lead to a higher voltage spike and higher problems in the lower frequency range. And the coupling capacity leads maybe then also in the higher frequency and the lower frequency range, depending on common mode. So difficult to say, and there's no perfect world for this, to be honest.
Okay, Andreas, thank you very much.
You're welcome.
So then let's just go on. In what case we need different values of CX, LC, M, or centimeters, probably, I don't know, in two-stage filter?
Yeah. This is the question where I showed you if you have a two-stage filter with different values. So this is maybe then a good choice if you have a broadband or a system which has a broadband EMI interference. That means you not only have big issues in the common mode, in the conducted range, but also in the radiated range. But so this maybe can be a good idea to say, okay, for the conducted range, I choose the manganese zinc and a bigger capacitor. And for the radiated one, I choose the nanocrystalline, the nickel zinc, or the air-gapped combo choke in combination with a smaller capacitor. So depending really on the EMI signature of your device. So because if I have really big combo chokes, for example, in my example I had one millihenry chokes. These are pretty small compared to other common mode chokes. But if you, for example, need 10 millihenry ohms, the influence in the very high frequency range is pretty poor of them. So maybe then it could be a good choice to skip one of the 10 millihenry chokes and add a smaller choke here for the higher frequency range, because the parasitic capacitance is smaller and therefore the frequency range which the core and the winding works as a filter is higher.
Okay, then let's go on with the next question. So I see there are a lot of questions coming in. That's really nice to see, a lot of interest here. If we can't answer all your questions now within this live webinar, we will answer them later on via email, or
yes,
Andreas will do.
I will answer every question.
So next question, varistors are also required for most main filters. Is there any help with the design?
Yes, in this app note I showed you at the beginning, I show you detailed how to calculate the varistor for a one-phase system. For a three-phase system, it's pretty much the same, just maybe the surge values are higher, not 2 kilovolt, maybe 4 kilovolts. Important is always, to size the varistor not too small from a diameter point of view. So 14 to 20 millimeter is always required. And then an important point is also where you place this varistor. It's not maybe only a good choice to place the varistor as like I did at the first place after the fuse, because then maybe you get during the surge event, depending on your inductive components in the system, a higher voltage spike. So in many applications can be also a good idea to place the varistor behind the input filter in front of the, for example, bridge rectifier. Then it has a better influence on the inductive spike, or sometimes also required to place two varistors, one before, one after, or damp this system with a capacitor which has a little bit lossy ESR. But as I said, in the ANP 015 in the new one, you can see how to calculate this varistor.
Okay, then here next question from Josef. The SNPS had a constant load or a dynamic load?
So a switch mode power supply has a constant load. So in the end, you should do, if you have only one, let's say, working mode, so when it's only continuous conduction mode, and then usually the good choice is to choose the lowest input voltage and the highest output current as a worst case. But if you have different working load modes due to light load, you have burst mode or DCM mode in your switch mode power supply, then you should do more than one measurement to really overcome all the working points of your system. So it's, because not always the highest output current means the highest EMC, let's say, noise signature in your measurement.
Okay, thank you very much. Then we have a very open question here, how to recognize a common mode or a differential mode noise.
Yes, therefore you can use, there are more possibilities. You can use a current clamp from Roland Schwarz with the required bandwidth. You feed both cables live in neutral through the current clamp, then you measure the common mode. If you only measure at one of the two cables, you have the differential mode over the spectrum, or you use the two-line listen I used here with a dual use output. Then you can see with the scope on, for example, channel 1, channel 2 minus each other. You have the differential mode with the math channel then, and channel 1, channel 2 plus each other is the common mode on the second math channel, for example. Then you see pretty good where is the main interference at which frequency.
Okay, so we still have a little bit more time, a lot of answers coming, thank you very much. So then let's go on. Is it possible to use LT spice for predicting radiated emission?
It's a common, let's say, to predict conducted emissions. Yes, we have already made a good video on YouTube for it. Anticipate EMC with LT spice is the name for it. So there you can see for up to 30 megahertz is pretty good. Then if you have, for example, automotive environment CISPA 25, you can have a listen which measure up to 108 megahertz. Then it's also good possible to predict here. Otherwise, it's getting a little bit difficult because in the over 30 megahertz for the standard industry, you measure the radiated spectrum, and then your cable length and the cable arrangement has a big influence here. And that's a little bit difficult. But what you can say is, if I'm getting in my simulation or in my measurements here on the test setup on the bench, I can measure here with the DC listen we also made together with Roland Schwarz. You can order this by Elector for €100, this DC listen, 200 megahertz spectrum. If you see there improvement of 20 dB at 100 megahertz on your test bench, you can really have a good result nearly to 20 dB at the radiated spectrum in the chamber, let's say. This correlates pretty good with each other. But otherwise, it's a little bit difficult because the cable has the biggest influence, and the impedance of the cable is depending on the length, and depending on which part of the cable you measure, you have different, let's say, standing waves and therefore different amplitudes. Easiest way is to have a listen here.
Okay. Next question is from Farhad. How to calculate and design the filter up front before designing the power supply?
Yeah, like I did here, always make a measurement without any filtering. Just make the pure power stage, maybe with a coupling capacitor primary to secondary, yes, or some other onboard, let's say, measurement. But if I would always do a first measurement on the test bench like I did here with my scope and the coupling plate without any filter components. Because only then you really know how big is the common mode and the differential mode, amplitudes, and after that you can start calculating. Because then you know how much damping you will need at which frequency. Because then you can start determining your corner frequency, start designing with 1 or 2 stage filter or whatever.
Okay, thank you very much. Welcome. Next question from Marian. Do we need any damping components in line filters, like input filter for buck DC-DC converter?
As I told you, maybe with a varistor, it can be necessary to damp this, that you have in very high, and you have let's say, common mode inductance with a very high leakage inductance, with a very high quality capacitor. Then you have two components with very high quality factors. Then maybe you can get a high ringing frequency or a ringing amplitude to the corner frequency of this filter. Then maybe it's really necessary to damp this a little bit with a series resistor of a second or of an additional X capacitor. But from a stability point of view, like we look at let's say negative input impedance as a DC-DC converter, where this can happen, oscillation, this is usually not necessary in most cases for the line filter. And it's also not the correct place maybe to damp, let's say, negative input impedance. There, you damp this usually at the input capacitor at the switch mode power supply.
Okay, so then I think we are coming to the last questions. Why aren't there damping resistors in the LC filters?
This what the same what I told you at the moment. When you have if I add damping resistors, then maybe I compromise if I have just one filter capacitor and put a damping resistor in series, then I will compromise my filter performance of this capacitor, of course. But I can add a second capacitor with a high ESR, electrolyte type. But this is a little bit difficult because the input line filters need to have VDE certificates, UL certificates, need to withstand some surge voltages and so on. So the components here compared to a pure DC-DC filter, they're only the biggest difference is safety, the compliance of these components, and the voltage rating of these components. So not that easy.
Okay. So then last question. How to compare the quality of EMI chokes?
The quality. Let's say the quality is maybe not the right point to look at. The impedance curve is interesting because in the end, it doesn't matter how much millihenry or microhenry or microfarad the capacitor or the choke has. The impedance curve is interesting. I need to have the filter choke a certain higher impedance than my system, and with filter capacitor I need a certain lower impedance at the required frequency. And this is interesting. So this is the reason why maybe an electrolyte capacitor is not a good choice, because his impedance curve is dominated by the ESR in a broad range, and therefore it's not a good filter capacitor. It's good for damping, good for hold-up time because of high capacitance, but not for filtering.
Okay.
So always look at the impedance curves, not at the pure values. Because the impedance curve, like in our combo choke, also starting to decay at certain frequency because of the frequency-dependent permeability of the core. And maybe the 3 millihenry or 3.3 millihenry that you do not have at 5 megahertz. It's only valid between 100 kilohertz and 2 megahertz. And then only then your calculation is valid if you really have in this frequency range where you calculate this, the component can hold his impedance.
Okay. So then, Andreas, thank you very much for all your answers.
You're welcome.
And also your presentation. And thank you very much for your attention. I hope you enjoyed our session today out of Munich. And yeah, then I would say stay tuned. We have some topics coming up and also with our partners today. And yeah, then I would say have a nice day. Thank you very much. And yeah, goodbye.
Goodbye.